In today's talk, we're going to continue what we've been doing in the last few talks and learn how to count orbits in a more efficient way. Remember, in our last lecture, we saw that the number of orbits, and here we're looking at the same problem. We're looking at the set of 6-letter strings, and we're looking at the action under the rotation group, which contains 6 elements, R0, R1, R2, R3, R4, and R5. That's rotation by either 0 units, 1 unit, through 5 units. We show that the number of orbits is the sum of the stabilizer numbers for each of the strings, and then we divide that sum by 6, the number of rotations. So we can write that like this, where stab x1, x2 through x6, the stabilizer number of this string is the number of rotations which fix this string. So we sum up the stabilizer numbers over all the strings, and then we just divide by 6. Now that's fine as a counting method, except when we have a large number of strings. This is not an efficient way to do things, and in a typical problem there'll be a very large number of strings. This isn't even necessarily more efficient than just listing all the strings and grouping them by their orbits. So the question is, has this helped us at all? And the answer is yes. It'll help us because we can take this sum here, the sum of these stabilizer numbers, and find a different way to express that. In order to do that, we'll have to start counting things a little bit differently. Here's a new definition. For each rotation, this is in our rotation group, R5. So each of our rotations, R sub I is 0 to 5 here, we'll define the invariant number, or inv of R sub I. Well, the book uses the notation little r sub I to be the invariant number of the rotation, capital R sub I. That will be the number of strings fixed by each rotation. So for inv, the invariant number for R sub I, it'll be the number of strings fixed by the rotation R sub I. And so let's look at an example of this. Remember, we're looking at 6-letter strings from a 2-letter alphabet. There are 64, which is 2 to the 6th, total strings. And we ask, what is little r0? That's the invariant number of the identity rotation R sub 0. Well, it's an identity rotation. It doesn't change any string. So there are 64 strings, or all of them, which are fixed by this R sub 0, R0. R1 is the invariant number of R1. I claim there are only 2 strings fixed by R1. The string AA, AA, AA. It should be pretty clear if you apply R1 to that. You get the same thing, AAA, AAA. And of course, there's also BBB, BBB. You can see easily that's fixed by R1. I claim those are the only 2 strings that are fixed by R1. Any other string, when you rotate it 1 unit, you change it to a different string. That should be pretty clear at this point. What about R2? That's a little trickier. What strings are invariant under the rotation R2? Well, I claim there are 4 of them, and let me show you how we can see that. Let's look at a 6-letter string. Here are the 6 positions for the letters in the string. Let's say we pick any 2 letters we want here. I'll call them X and Y. For it to be invariant under R2, when you apply R2 to that, you take this XY and you move it to the end. And that has to be the same thing you started with, so this has to be an X and a Y in order for R2 of the string to equal the original string. And of course, if this is an X, if this is the same string we started with, when you apply R2 again, you'll get the same thing, and that tells us we also have an XY here. So the only way to get a string that's invariant under R2 is to choose the first 2 elements, whatever we want, A's or B's, and then just repeat the choice of the first 2 in the second 2 and in the third 2. And how many ways can we choose the first 2 elements of the string? Well, there are 2 choices for each, so we have 4 total choices. These could be AB, it could be BA, it could be AA, it could be BB. So we have 4 strings that are invariant under R2. Notice it's fine. The string AAA is invariant under R2. It is invariant under R1. It also is invariant under R0. It's counting in all of them. But we have 4 separate strings invariant under R2. What about R3? Again, let's look at a 6-letter string. For it to be invariant under R3, when we apply R3 to it, we take these 3 letters in the string and we move them to here. And the idea is that the new thing we get has to be the exact same as the original thing that we had. And how is that possible? That means if whatever we have here, I'll call it XYZ, you're going to need, after we move it, the first 3 letters to be the same, so we're going to need an XYZ here. And if that's the case, then of course after we move it, you'll have XYZ over here. So you really will have a string invariant under R3. So how many ways are there to choose a string that's invariant under R3? We can choose X to be anything we want, meaning A or B. Y can be anything we want, A or B. And Z can be anything we want, A or B. We'll have 2 times 2 times 2 choices, or 8 total strings that are invariant under R3. And let's just compute the, this is actually a mistake I put. We'll see that. I don't know why there was the number 4 there. R4 I claim is 4. Why is R4 4? Well, I'll make the argument without even writing anything down. A rotation by 4 units is the same as a rotation by 2 units in the opposite direction. And because of the symmetry here, a rotation by 2 units in the opposite direction is functionally the same when it comes to counting which strings are invariant as a rotation by 2 units. The rotation R2 by 2 units to begin with. If you think of this as people seated around the table, the initial R2 corresponded to moving the pointer to where the head of the table is 2 units clockwise. R4 corresponds to moving the pointer 2 units counterclockwise. You can see that they'll have the same number of invariant strings, so R4 is just 4. And for the same reason as that, R5, which is the invariant number for R5, I see why I had that typo there, that's just 1. I claim R5, not 1, sorry, 2. It should be the same number as R1. Why? Because this rotation by 5 units is the same as the rotation by 1 unit in the opposite direction. So again, it should have the same number of strings that it fixes as R1. So now we've corrected it. We have the correct invariant numbers for all of the different rotations here. The invariant numbers are 64, 2, 4, 8, 4, and 2. Now, this might seem like an odd diversion, but you'll see it will help us understand an important counting principle that will let us use these invariant numbers. So I'm going to ask you this totally off-the-wall question. How many funerals do you expect to go to in your lifetime? And not necessarily you, but say for a typical person in the US. That seems like a very odd question, and certainly for young people, I would bet that almost all young people kind of underestimate that number. So think in your head what that number would be, how many funerals you're expecting to go to over your lifetime. Let me ask you now a different question. What's the average size of a funeral in the US? I've looked this up and the numbers kind of vary that I get, but I'm getting anywhere from 30 to 50. Let's just say 50 is the average size of a funeral. When you go to a funeral, there are typically about 50 people there. Some are much, much bigger. Some are quite a bit smaller than that. Now, how do these two numbers relate to each other? Well, let's just look at what happens in a funeral. Here we have the casket, maybe, if the casket's there in the funeral, and here we have a bunch of people. I'm not going to put 50 people here, but we've got a lot of people here at the funeral. I claim that the number of funerals you're expected to go to in your lifetime should be the same as the average size of a funeral, that these two numbers should be the same. So if the average size of a funeral is 50, then that tells us that the average person in the US should go to about 50 funerals in his or her lifetime, which should seem like an awful lot to you guys, because at your age, when you're around 20 or somewhere in your 20s, you probably haven't gone to many funerals at all. Maybe one or two, but you're thinking these are very rare things that you'll go to. And I can say I've seen this as I've gotten older. When you get old, of course, that's when you start going to a lot of funerals. Sadly, I've been to a couple in the last 2 years. And 50, once you get older, you see that 50 is actually a reasonable number that you can expect to go to in your lifetime. The best way to end up going to many fewer is to die young, which is really not a good solution, because then you miss out on a whole lot of other things. But if you live, obviously, if you live to an older age, you'll be somebody who probably goes to a lot more funerals. Now, what I said will be true if we make a few simple assumptions that say over time, and here we have to talk about over an entire lifetime, that traditions or customs in the US don't change that much, so that funeral sizes stay about the same over that entire period of time. And of course, the reason I picked funerals instead of things like weddings is that each person can be expected to have exactly one funeral. You don't get to have multiple funerals. The funeral is dedicated to just you by yourself, and you get one of them. So why should it be that the average size of a funeral is the same as the average number of funerals that you would expect to attend in your lifetime? The answer is this. Look at a single funeral. Every time when you see a funeral with some number of people in it might be approximately 50, but it could be any number. Every time a person goes to a funeral, we have two ways of counting that attendance, your attendance at the funeral. You could think of your attendance of the funeral as giving a +1 to your funeral count, and it will do that for every single person at the funeral. There'll be a +1 for how many funerals you go to. Another way to do that, and again, let's assume there are 50 people here. Let's put the ... You could count for the funeral, you could count a +50 in the funeral column. If we look at all the funerals that go on in the country over a long period of time, and we count up the total number of attendances at funerals, meaning how many individual people attend the funeral over all these funerals, we could have two ways of counting that number. We could count it by looking at each funeral and adding up the total attendance at each and every funeral over all the funerals that happen. Or we could instead count up over all the people and just look for each and every person how many funerals they've attended. Either way, we'll get the same total number of funeral attendances that happen. So we can sum up either grouped by funeral or grouped by person, and we get the same thing. And I claim that's exactly what we can do in this mathematical problem that we're facing now when we're counting orbits. We have to sum up. We've already seen that the number of orbits is just 1/6 for the problem we've been working on, 1/6 the sum of the stabilizer numbers for all the strings. I claim if you sum over all the strings, in this case we have 64 strings, you sum up their stabilizer numbers, you'll get the exact same thing as if you sum up over all the rotations. Here we just have 6 rotations, R0 through R5. You sum their invariant numbers. Why should you get the exact same thing? Well, think of all the different rotations, 6 of them, and all the different strings, 64 of them. For all the different rotations acting on all the different strings, every time a rotation fixes a string, that counts as a +1 in the stabilizer of that string. it also counts as a +1 in the invariant number for that rotation. And then you just do this every single time for any string which fixes any rotation. You'd be adding 1 on each side every time that happens. So you get the same total number. It's the same basic principle. It's a duality principle that you can sum up either by strings counting their stabilizer numbers, or sum by rotations counting their invariant numbers. So what's our conclusion? Our conclusion is that because the number of orbits was 1/6 this sum of the stabilizer numbers, the number of orbits now is 1/6 times the sum of the invariant numbers. And for the problem we're working on, which has strings of length 6 from a 2-letter alphabet, there were 64 strings. It was a lot of work, and we went through this in the previous lecture, adding up all the stabilizers and taking 1/6 of that. But now there are only 6 rotations. All I have to do is take the average 1/6 of these invariant numbers, and we had those just 2 pages earlier. These numbers here on the left, I'll just remember them for you. They were R0 had invariant number of 64, then R1 had 2, then R2 had 4, then 8, then 4. This is for R0, R1, R2, R3, R4, and R5 was 2. And if we add those together real quickly, that's 64 plus 2 is 66, 70, 78, 82, 84. We have 84, that's equal to 84 over 6, which is exactly 14. And you'll remember a couple lectures ago, we actually counted all the orbits, and it was exactly 14 orbits. Now, this principle that the number of orbits is 1/6, 1/6 the sum of the invariant numbers. And here, the importance of this 1/6 is that 6 is the size of our rotation group, the number of rotations, is that this is a special case, special application of Burnside's lemma. This was pointed out by Sarah in our discussion section. Burnside's lemma applies anytime you have a symmetry group or some group acting on some set. Here we have a group of rotations acting on this set of strings. If you haven't studied group theory, don't worry about this lemma in general. But what the lemma says is the number of orbits that you count, exactly what we're counting here, the number of orbits for the different elements in your set that are acted on by the group, the number of orbits is exactly the average of the invariant numbers for the members of the group. Invariant numbers are defined the same way. The invariant number for a group element is just the number of things in our set that that group element fixes. So it applies to any group when you're talking about its action on a set. And this lemma of Burnside's, I didn't even know this until I looked it up. Now I've used this lemma and taught it before, but I didn't know that this lemma is often known either as Burnside's lemma or, quote, the lemma that is not Burnside's, which might seem like an odd name, except this is a reasonably common phenomenon in mathematics that Burnside didn't. He wasn't the first one to use or prove this lemma. He didn't even claim to be. It was in his book, and he gave attribution to somebody else. I think it was Frobenius, and it was known before Frobenius. It was known by Cauchy even earlier. So Burnside didn't call it his own lemma. He certainly was just using somebody else's lemma. It's just somebody later read his book and just started calling it Burnside's lemma, and then other people noticed that and said, okay, we'll just call it the lemma that's not Burnside's. Let's look at one other example different from the one we've been working on, though this is an example we did look at in our discussion section. Consider strings of length 4 from a 3-letter alphabet ABC. Remember, this will correspond to seating arrangements of 4 people around the table, people of color A, B, and C, say red, green, and blue, something like that. Here we have one possibility, A, B, C. That would correspond to the string A, B, C, if we're starting They're up at the top and going around clockwise. How many strings are there of length 4 from the 3-letter alphabet? Well, there are 3 to the 4, which is 81 strings. And our question is, how many different table arrangements are there? Well, we consider 2 table arrangements the same if you can rotate one to get the other. And that's the same as asking the question, how many orbits are there among these 81 strings under the action of our group of rotations, which consists of R0, R1, R2, and R3. Just rotate by 0 units, the identity, rotate by 1 unit, rotate by 2, and rotate by 3. Well, now using our new counting method, all we need to do is compute little r0, little r1, little r2, and little r3. These are the invariant numbers for these rotations. And we ask how many of these 81 strings are fixed by r0. Of course, the answer is easy. It's 81. R0 doesn't change any string. It leaves them all alone. So every single string is fixed by R0. That's certainly the easy one. But it's also easy to tell how many strings are fixed by R1. The only ones that are fixed by R1 are A, B, and C. There are just 3 strings that are fixed. And remember that a simple reason why is if a string is fixed by R1, then this will have to be the same as what you get when you move the first letter to the end, which means whatever this first letter is, the second letter will have to be the same thing. And then by the same argument, whatever the second letter is, the third letter has to be the same, and the fourth letter will have to be the same. And just as before, we can find R2 very easily. That's just 9, because if we have 4-letter strings and we want it fixed under R2, we want it to be the same when we take the first 2 letters and move them to the back. Whatever these are, then they'll have to match these, X, Y. And there are going to be 9 ways to choose the first 2 letters of the string. The second 2 will just be forced then to match them. 3 times 3 gives us that 9. And just as we saw before, R3 has to be the same as R1 because a rotation by 3 units is just like a rotation by 1 unit in the opposite direction. So I'll have the same number of strings that get fixed. So what is the total number of orbits? It's just 1/4 because we have a group of size 4. We take the average over the entire group. Of these invariant numbers, 81 plus 3 plus 9 plus 3, 81 plus 3 plus 9 plus 3 is 96. 96 over 4 is 24. We have exactly 24 orbits. And if you remember in our discussion section, we tried to organize them in a way so we could count them all, and we ended up, after a little bit of fussing around, with exactly 24 orbits, but it was becoming a big mess. And it was already becoming a big mess to do this just by direct enumeration, even when we had just strings of length 4 from a 3-letter alphabet. Imagine if we had strings of length 12 from a 6-letter alphabet. It would be huge. There would be no way to deal with that, and yet you can use this method rather simply to compute the total number of orbits. So that tells us 24 orbits. We have 24 different ways to seat A's, B's, and C's around a table where no 2 are the same, meaning no one can be rotated to get another.